Hello viewers, Daruna taking you through the story for A-Level Physics Paper 1. And this video, we're going to go through the marking guide of Senior 5 Physics Paper 1 for end of term 1 for the year 2024. So this video is suitable for students in both Senior 5 and Senior 6 offering physics as part of their combination. So these are some of the papers we hope to upload. So this holiday we are interested mainly on Senior 5 students. That's why I'm uploading past papers from different schools, e.t.c, Gayaza, King's College, Budo, and Mengo SS also. So I'm interested more in Senior 5 because A-Level is somehow different from O-Level. So I welcome you to A-Level. How was your first term? I think you must have realized that in physics, A-Level physics, there are no longer objectives, they are no longer structured questions, so everything is essay. That means that there's need to be a change on how you present your solutions. What usually disturbs us is the way you present your solutions. It is one thing. So we shall upload a number of videos so that you get used to an A-Level style of answering questions. There are also books you'll need, so you can't go through A-Level without these books. They are the ones we recommend because I have a bigger hand in their writing. So there's math from Principal Math. There are 4 books: Math Paper 1 notes, Math Paper 2 notes, Topical Question Bank for a number of years, 2023 up to 1988, and also Termly past papers with marking guides. So these Termly past papers with marking guides are updated every year. So I think once this is released 2024, meaning that every year we update. Now these questions I'm uploading on this video, they'll be compiled in the book for 2025. So I encourage you to get these 4 books for you to be contented that now you have all the material needed for A-Level mathematics. For subsidiary mathematics, there is only one book which has notes, Termly past papers with marking guides, and also U.A.C.E past papers with marking guides, and reports, of course. So even this one has reports. Remember, U.A.C.E has to write a report on the performance of students, how they fared, what was their weaknesses, and the advice. So this book contains those U.A.C.E past papers and reports. It is a little different from these solutions books you've been buying, because those solution books only have solutions, but here we provide marking guides, how marks are awarded, and 2, we also provide a report. What was the weakness of candidates in that year, and what advice should be given to candidates and teachers? So this book contains all that. Therefore, I encourage you to get those 4 books for you to be contented that you have all the materials needed for A-Level mathematics. Same applies to physics. We have Physics Paper 1, Physics Paper 2, Topical Question Bank, and their solutions. So if you need copies, contact the author on this contact. And the genuine book must have a hologram, or what we call a seal, on the top cover of the page. I think in the next video I'll show you the picture of how the hologram will be. And that hologram should be scannable by a QR scanner. So if you go with your phone to buy, you can try to scan it and see. So next video I'll show you, I think, how that hologram looks like, so that you don't just buy books which are not genuine and which are not updated. Then also, I think I need to show you how you can navigate through the YouTube channel. So let's do that. So what you need, you have to go to any browser. Let me choose this. That is if you're using a laptop. If you're using a phone, still you'll need to go to an app called YouTube. If it's not there on your phone, but I think it is there because you'll also watch videos. But if it's not, then you have to install it from your Play Store. So on laptop, you have to look for this YouTube, and then you can search the channel name Rowa. Okay, here it has come, but let me assume it's the first time. So you have to search Rowa e-learning. Even if you stop there, this picture will come, so you double click on it and it'll take you to that. So there are 4 options. There is videos. That one shows the videos in order of uploading, and there are also playlists, which are folders where a number of videos are kept. Then we have home. Now home is our interest, because there the different folders are categorized depending on their likeness. For example, if you look at this A-level applied math, it contains only math paper 2 videos. O-level math, it contains only O-level math videos. O-level physics contains only O-level physics videos. Then A-level pure math contains only math paper 1 videos. A-level physics part 2 contains only A-level physics part 2 videos. Like that. So, and also there's also subsidiary math. Then there's A-level physics part 1, contains only physics part 1 videos. And also, and past papers with their marking guides for a number of years since 2022. Then here we have national math contest videos for O-level. We are yet to upload the ones for A-level. So those who can attempt in math contest, how was it? Hope you qualified for paper 2? If not, next time better. So basically that's how you can navigate through the YouTube channel. And now we can now go back to our solutions. So here there was two sections, section A for mechanics and section B for heat. So question 1, part A, Roman 1 says, what do you understand by dimensions of a physical quantity? So you come to the dimensions of a physical quantity is the way that quantity is related to the basic quantities, which are mass, length, and time. So in A-level, you don't have to rewrite the question, you only write the solutions, but make sure your solutions are well identified. So that was Roman 1. Then Roman 2 says, state any 2 applications and any 2 limitations of dimensional analysis. So let's begin with the applications. 1 is used in unit conversion and dimensional consistency. So this helps us to convert units and ensure consistency of equations. 2, it helps us to check the correctness of physical equations. So we can use it to verify whether a physical relation is dimensionally correct. So that was about applications, but they also ask for limitations. So limitations 1, dimensionless constant. So dimensional analysis cannot determine dimensionless constants in equations. Then you remember, dimension of a constant is always 1. So you cannot. So this dimensional analysis cannot help us to identify dimensionless constants. Then 2, there are some functions which are complex, so it cannot handle equations involving trigonometric functions, exponential functions, logarithmic functions, and so on. So basically those are the applications and limitations of dimensional analysis. So that was part A. Now we shall go to part B. Part B says the viscous force capital F acting on a spherical body of radius r falling through a fluid of coefficient of viscosity mu is given by this. So I think they didn't define V, but V is velocity. So you can add it there when you're writing the question. Use dimensional analysis to find the values of x, y, and z, where mu, dimension of mu is this. So shall come and code the formula given, then we put box bracket. It must be box bracket to main dimension. So this means I want to get dimension of f, dimension of a constant, dimension of mu, dimension of r, dimension of v, like that. So dimension of f will be this. A constant is 1, mu was given in the question, r is length, and v is velocity. Then use the laws of indices to open the brackets. When I open the brackets, this becomes this. So you realize that m, we have m to power 1. I think that is the only one. So 1 times x, that is why you get m to power x. When it comes to L, this and this gives you negative x, this gives you positive y, and this gives you positive z. That's why you have negative x, positive y, positive z. For T, this gives you negative x and this negative z. That's why you have negative x, negative z. So let's just see the marks for this slide before we go to the next slide. So this dimensions for left hand side, dimensions for right hand side, and equating the two. So now I'll start equating indices of m, l, and t. Let's start with the ones of m. So when you go to the ones of m, you'll realize that, let me see here. Here m is power 1, here m is power x, meaning x is equal to 1. So I'll come here and say that x is equal to 1. Then equating indices of t, I'll come here and see where is t. T here is negative 2, and here t is negative x minus z. So I'll come and equate those two. The good thing I really know the value of x. So I'll come and substitute for x here and be able to get the value of z. The next is to equate indices of L. So I'll come back here and look at L. L has power 1 here, and here it has this. So I'll come and equate them. So when I equate, the good thing I know the value of z, I know the value of x, so I'll come and substitute and get the value of y. So basically that is what they wanted. And that's how we could get the 4 marks. Now we shall go to part C, Roman 1. Part C, Roman 1 says, define the term displacement. So displacement is the distance traveled by a body or a particle in a specified direction. That word specified direction must be there, because it's one which distinguishes distance from displacement. Then Roman 2 says, a car initially traveling at a velocity capital U is acted upon by a constant force for some time, and after covering a distance s, its velocity changes to v. Show that the distance s covered by the body under the action of the constant force is given by this. So I think we realize that this is third equation of motion, but they just made s the subject, where a is the acceleration of the car. So in short, we have to derive the expression for the third equation of motion. So you come and say that average velocity is given in two ways. One, it can be displacement over time, or it can be sum of the two velocities divided by 2. But they want us to make s the subject, so I'll bring this to this side to come up with this. Then I'll remember that first equation of motion is given by this. So when I make t the subject, I'll come up with this, which I can substitute here. When I substitute, I'll come up with that. Then I realize that this numerator is difference of two squares, which is v squared minus u squared, and the denominator is 2a, and that's what they wanted. So that's how you could get the 1 mark for this and 4 marks for that. Now shall go to part D, Roman 1. Part D, Roman 1 says, an object is projected vertically upwards with a velocity of 20 meters per second from the top of a building of height 50 meters. Sketch a distance time graph for the motion of the object. So here it was supposed to be 2 marks and here 4 marks. But I should adjust that in the solution. So they want you to sketch the distance time graph for the motion when a body is thrown vertically upwards, and it moves upwards and then comes back to the ground. So you shall need the axes and label them. They said distance time graph, so distance is vertical, time is here. They said it starts from a cliff. Let's first read the question. It starts from a cliff of a building of height 50 meters. So the starting point will be 50, then it moves vertically upwards. So as it moves, because of acceleration due to gravity acting downwards, its distance keeps on reducing as time increases. This is now the maximum height where it is momentarily at rest. This is not changing, but time is moving. Then from that, it now goes down with an acceleration. That's why it now goes up. So I want you to realize something. This to this, but it exceeds a little. Why? Because from here to here, it has now reached the point where it started from, but now it continues going downwards. So that's why it goes an extra distance. One is that this graph is drawn with freehand. So other graphs for which they can ask can be velocity time graph for that motion. Now here, these graphs are a little different from this. Do you see something? This began from 50 because it was at the top of a building. Now here, it just begins from the level ground and it comes back where it started from. That is why when you are drawing it, you see this line, it should be equidistant. So from here, tier must be equal to from here, tier. Same applies to this. From here, tier must be equal to from here, tier. Same applies to this. From here, tier must be from here, tier. That is if it was projected from a level ground. So let's take note of that. So those are the different kinds of graphs which they can ask. Then Roman 2. Roman 2 says, find the time taken by the body from the point of projection to landing on the ground at the foot of the building. Okay. So we shall use second equation of motion, substitute, because it is below the point of projection, that's why it is negative. Here we shall put negative because, why is it negative? It is because the body first moved upwards, meaning that acceleration was negative g. And here the funny thing is that in O level you used the g as 10, but in A level it depends on the subject. For applied math, g is 9.8, and for physics, g is 9.81. So don't confuse the two. Then we shall simplify. This times this gives this. So that means we have got a quadratic equation which can solve to get the two values of t, but t cannot be negative because the particle began moving when t is 0. So t can be negative, therefore t is that. And basically that's what they wanted. That was question 1. Now we shall go to question 2, part A, Roman 1 says, differentiate between scalar and vector quantities and state 4 examples of each. So one shall say that scalar quantities are physical quantities which have only magnitude, while vector quantities are physical quantities which have both magnitude and direction. So examples of scalar quantities can be work, power, speed, distance, temperature, area, volume, charge, kinetic energy, pressure, among others. So they want any 4. Then examples of vector quantities can be displacement, velocity, acceleration, force, electric field, momentum, among others. So any 4 is okay. Then Roman 2 they said, what is meant by resultant vector? So a resultant vector is a single vector that has the same effect and is equivalent to the given set of vectors. It must be one vector and has the same effect as the given set of vectors. And that's so here in the first 2 got have a mark, the next 2 have a mark. Also here first 2 have a mark, next 2 have a mark. And basically that's how we could get the 4 marks in Roman 1 and 1 mark in Roman 2. Now we shall go to part B, Roman 1. B Roman 1 says the figure below shows 4 forces, okay, of magnitude, these ones, acting on a particle of mass 50 kilograms. This is it. Find, Roman 1, the magnitude and direction of the resultant force. So we are going to first redraw, because in resolving it is advisable that you get angles lying on the horizontal. So yeah, if this was 100, it means that, and this is 60, it implies to get 90, you are left with 30. And because the whole of this is 100 minus 30, you get 70. And because this is 90, 190 minus 70, you get 20. So the aim of redrawing is to get angles to the horizontal. Then that will be easier to resolve, because you will know that horizontal components will have cos and vertical components will have sine. So this is the entirely horizontal, that's why you see no vertical component. And also this is entirely vertical, that's why you see no horizontal component. The rest, there will be cos on the horizontal and sine on the vertical. Then the negative depends on the whole. From here, I think you can see, to move in this direction, you move to the left, then upward. Now left means negative, it's here, and upward means positive. For this one, downward is negative, like that. So the only way to bypass the positive and negative is to measure all angles starting from the horizontal. But that may be disturbing. Let's first leave it in that case. So next is to use a calculator to get the answers to 4 decimal places. Then you get the magnitude from Pythagoras theory, and then the direction. Direction, you have to draw a right angle triangle. So positive horizontal is that, positive vertical is that, then line from start to end is the resultant, and we also need the direction. So you can use SOHCAHTOA, where tan is opposite over adjacent, to give you the value of theta to 2 decimal places. So angles are written to 2 decimal places. Then you can state that the magnitude is that, acting in the direction that, above the positive horizontal. And basically that's what they wanted in Roman 1. Then for Roman 2, they said that distance covered by the particle in 5 seconds, given that the particle was initially at rest. So one shall remember that from Newton's second law of motion, F is equal to ma. We have got the resultant, we have the mass, we can get acceleration, which is that. Then from there we can come to second equation of motion, substitute u, which is 0, time taken, g, which is a constant, time taken. Then from there I can know the distance traveled. Then for part C says a particle is projected vertically upwards, and after a time t, another particle is projected vertically upwards with the same initial velocity from the same spot. Prove that their velocities when meeting will each be a half gt. So first we need to make a sketch for us to easily go about with the proof. So this is the first particle projected and the second particle they meet at this point D. So let's call it a height h, and this will be the maximum height h max. Then the initial velocity, they said they were projected with the same velocity, so this will be u and that will be u. So for the first particle, that is motion A through C to D, initial velocity is u, which is here. Time taken is capital T, let it be capital T, and the displacement is h. Remember, displacement is from the starting point to where the particle is. Therefore, second equation of motion, I can substitute for u1, t1, s1 to come up with equation 1. Then for the second particle, remember the second particle, they told us something. They said the second particle is projected after t seconds. Okay, after t seconds, the second particle is projected. So meaning that if this one took a time capital T, what time did the second particle take? It must have taken less time. So shall come here and say, okay, let's first see the marks for this slide. So shall come here and say that for the second particle, that is motion BD, AU is that, T is that, and S is that. So I can quote the second equation of motion and substitute. That will be equation 2. So I can now substitute equation 1 into equation 2, where there was h will be replaced with this. Then I expand this to give me this. Open now brackets. I'll come up with that. So this negative with this negative gives positive. Negative with positive gives negative. Then I realize something, that this can cancel and also this can cancel. So I remain with that. I remain with this, and this. Then I also realize that t is common, small t is common throughout. So then I'll come and remove one t to remain with that. Remember, now I've somehow got what they want. Remember, they want this one. Okay, so I'll try to put it on one side and take this on the other side. So this one is somehow familiar because we know that from the first equation of motion, if v is the velocity of the first particle at the point where they meet, it means it is downward. Okay, now because it is downward, it means that v is equal to u minus gt. So I'll come and substitute for this, replace this with v. You'll come up with this. And I think we have proved because they wanted the velocity at the point of meeting. Why is it negative? It is because the first particle at that point of meeting is moving downward. That's why there's a negative sign, meaning that the second particle will now be moving upward. And that's what they wanted. So basically, that's how you could prove and get the 7 marks out of this question. Now we shall go to section B, which is under heat. Question 1 says, part A Roman 1, distinguish between ice point and steam point as applied to temperature. So we shall come and say that ice point is the temperature at which ice and water coexist in equilibrium, but at a standard atmospheric pressure. So don't forget this word. While steam point is the temperature at which steam and water coexist in equilibrium at a standard atmospheric pressure. So that is the standard definition of this difference. But you can also distinguish them in this way, that ice point is the temperature at which pure water freezes into ice, while steam point is the temperature at which pure water boils into steam at standard atmospheric pressure. So any of the two is okay. That was A Roman 1. Now shall go to A Roman 2. A Roman 2 says, define the term thermometric property and give 2 examples of thermometric properties. So thermometric property is a physical property of a substance whose value varies linearly and continuously with temperature. Linearly, continuously with temperature must be seen. Then examples can be electrical resistance of platinum wire, EMF across junctions of a wire, length of a liquid column in the stem of a thermometer, pressure of a fixed mass of a gas at constant volume, volume of a fixed mass of a gas at constant pressure, wavelength of radiant electromagnetic waves. And basically that's what they wanted. Then now shall go to part A Roman 3. A Roman 3 says, state any 2 desirable properties of a good thermometric property. So a good thermometric property should 1. Vary over a wide range of temperature, 2. Vary linearly and continuously with temperature, 3. Should be sensitive to temperature changes, and 4. Should give a single value for a certain temperature. Then it should accurately be measurable over a wide range of temperature for simple apparatus. So any of the 2 is okay. Now we shall go to part B. Part B says, describe how a constant volume gas thermometer can be used to measure the temperature of a body on the Celsius scale of temperature. So there we shall need to draw a diagram of a constant volume gas thermometer and then be able to use it to explain how it works. So this is a bulb, this is a reference mark, that point you see here to help you identify the level. Then this is the atmospheric pressure, mercury, difference in levels of mercury, and flexible rubber tubing. So you can label it: glass bulb, dead space, movable tube, mercury, flexible rubber tubing. So any 4 labelings which are correct and the correct diagram, you get the 2 marks. Then the other 4 will be got from the body of the description. So you start by saying that a constant volume gas thermometer is as shown above to connect what you're going to write to the diagram. Then the bulb containing the gas is immersed in an enclosure whose temperature is to be measured. Okay. Time is allowed for the gas to acquire a temperature of the enclosure. Okay. After that, the flexible rubber tubing is adjusted to bring mercury levels to the reference mark R. I think you see that. When that is done, you can now measure the difference in the mercury levels H. The gas pressure P theta will be equal to H plus or minus small h, where H is the atmospheric pressure. We are saying plus or minus because, let me see here, it depends on this difference. The difference can be below. For example, here it means that the pressure at this point is equal to this plus this. Okay. What if you adjust and you realize that the level of this is down here? It implies that the pressure at this point will be what? It will be atmospheric pressure minus this, because pressure increases with depth. And that is the reason why we're saying plus or minus small h. The bulb is then immersed in ice-water mixture and the pressure P0 is obtained. So before we complete the CMAX for this slide, then we can go to the next slide. It is then immersed in steam and pressure P100 of the gas is obtained. The unknown temperature can now be calculated from this expression. And basically that's what they wanted. Then part C, Roman 1. Part C, Roman 1 says, the resistance R theta of platinum varies with the temperature theta as measured by the constant volume gas thermometer according to the equation this. Okay, Roman 1. Calculate the temperature on the platinum scale corresponding to 60 degrees on the gas scale. Okay, so we shall come and say that is the given equation. So we shall get temperature at 0. When theta is 0, we shall come up with that resistance. When theta is 60, come up with that resistance. When theta is 100, come up with that resistance. Then from there I can quote the formula. Substitute R60, R0, R100, R0 times 100 to give you 56.4 degrees Celsius. And that's what they wanted. So now we shall go to part C, Roman 2. Part C, Roman 2 says, account for the difference between the values and state the temperature at which they agree. So the difference between the two values is because platinum resistance thermometer and constant volume gas thermometer have different thermometric properties. Remember this one, platinum resistance thermometric property is resistance of platinum wire, while constant volume gas thermometer, the thermometric property is pressure over fixed mass of a gas at constant volume. So they are different, meaning that they vary differently with temperature changes. The good thing is that they can agree at the extreme, or at the fixed points, that is ice point and steam point. And that's what they wanted. Then now we shall go to question 4. Part A, Roman 1 says, when are two bodies said to be in thermal equilibrium? So two bodies are said to be in thermal equilibrium when their temperatures are the same, or when there is no heat flow from one body to another, or you can say when the systems are stable and have reached a balanced state. They wanted only one, so any one is okay. Then now shall go to Roman 2. Roman 2 says, outline the steps necessary in setting up a Celsius scale of temperature. They just told us to outline, not to describe. So we shall come and say, a thermometric property is selected. You need to know the thermometric property. For example, for a constant volume gas thermometer, thermometric property was pressure over fixed mass of a gas at constant volume. Then from there, you have to get the value of that thermometric property at steam point. Also get its value at ice point. And also get its value at the unknown temperature. After doing that, you can now calculate the unknown temperature using that formula. And basically that's what they wanted. Then part B, Roman 1. Part B, Roman 1 says, with the help of a well-labeled diagram, describe how a platinum resistance thermometer can be used to find an unknown temperature on a Celsius scale. So just like we did for constant volume gas thermometer, even here we need to draw a labeled diagram. So here we shall need a Wheatstone bridge. So let's first draw a Wheatstone bridge. Then put fixed resistances and a rheostat here. Then shall put the leads. There is a dummy lead of resistance R, shorted at both ends. Shorted. Shorting means connecting the two. Then here we shall have also an insulator with copper leads of resistance R. So I think you realize something about this resistance. They are the same. Joined to platinum wire, so we shall wound platinum wire on this insulator. And that will be platinum wire of resistance R theta wound on an insulator. Then you shall need an enclosure. That will be a silica tube. Okay, so 2 marks were for the diagram, then the remaining 4 marks were for the body. So we shall come here and try to write something on the body. 1, we shall begin by saying that a resistance thermometer is connected to one arm of the Wheatstone bridge consisting resistances R1 and R2 which are equal. Okay, I think you know why they are equal. So the thermometer is immersed in the ice-water mixture and the rheostat RS adjusted until balance point is reached. the reading of the rheostat at balance point is noted and it will be equal to the resistance R0 of the thermometer at ice point. Okay, so that is the reason why these two were made equal. Is the reason why these two resistances were equal. So that this and this arm, they are also equal. Why are they equal? It is because each of these, okay, let me do something here. This one has a resistance of R theta plus small r. Okay, this one has a resistance Rs plus small r. Do you notice something? So that means that if the small r goes away, it implies that Rs will be equal to R theta. So each value you'll be reading here will be equal to the resistance of this platinum wire. That's the logic behind. So the thermometer is then immersed in steam and the procedure is repeated to get the resistance at steam point. Then you bring the thermometer in contact with the body of unknown temperature theta and repeat the procedure to get the resistance at unknown temperature. Then from there you can now get the unknown temperature from the formula, that one. And that's what they wanted. That was B Roman 1. Now we shall go to B Roman 2. B Roman 2, it says, the table below shows the values of resistance and pressure read from a platinum resistance thermometer and constant volume gas thermometer, respectively, at ice point, steam point, and unknown temperature theta. This is it. So platinum resistance thermometer, constant volume gas thermometer. Find the value of theta on the platinum resistance thermometer and constant volume gas thermometer and account for the difference in the value of theta. Okay, so we shall come here and say, for the platinum resistance thermometer, theta will be given by this formula. Then you substitute R theta, R0, R100, R0 times 100 to get that. For the constant volume gas thermometer, formula is in terms of pressure. So P theta, P naught, P 100, P naught times 100 to get that. So they are different. Why are they different? Is because these two have different thermometric properties which vary differently with temperature changes. So they only agree at fixed point, like we already saw. And basically that's what they wanted. So this statement was not needed, or was not necessary. So now shall go to part C. Part C says, Roman 1, define the term triple point of water. So triple point of water is the temperature at which pure water vapor, and pure ice are in equilibrium. You can say coexist in equilibrium. Whatever is okay. Then Roman 2, when is the temperature 0 Kelvin attained? So 0 Kelvin is attained when molecules of a substance have their minimum total energy. And at that point, it means that molecular motion nearly ceases or stops. And pure substances can ideally form perfect crystals with no structural imperfections. And basically that's what they wanted. So that brings us to the end of this video. Thanks for watching, and be reminded the next video will be now for Math Part 2 done by Mengo. Senior Secondary School. So if you are not yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video has been uploaded. And also, if you know of any student who's not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp so that you can all benefit as a family.